For more than 40 years, Mark Wirfs has helped the grain industry address its electrical needs. With a partner, Mark created R&W Engineering, which has offices in Beaverton and Bend, Oregon, and Longview, Washington. With his colleagues and staff of 36, Mark provides electrical, mechanical, and automation engineering services. He holds a Bachelor of Science degree in electrical engineering from Oregon State University. Mark has worked on a wide variety of power, lighting, and automation systems at grain handling facilities in Oregon, Washington, and California, as well as British Columbia. Some of his clients have included the former Continental Grain, Harvest States, now United Harvest, United Grain in Vancouver, and Temco LLC in Portland and Tacoma. Mark has been a Jeeps Associate member for 35 years and represented Jeeps and NGFA as the primary delegate on the National Electrical Code Panel number 14. He is a past president of the Oregon chapters of the Institute of Electrical and Electronics Engineers and the American Council of Engineering Companies. Additionally, Mark is also a member of the National Fire Protection Association. Please welcome Mark Wirfs.
Thank you.
I need to set your timer again. Just so you.
We are going to go through that. And my presentation includes the whole gamut of also the front-end planning of how you would plan an electrical system for any type of a grain handling facility. Of course, that can run quite the gamut from a small transfer facility to an export grain terminal. So obviously there's a lot of different ways to look at that to cover facilities. So, your typical power systems that you get into, we call it the 600 volt class systems and the codes and so forth. Get into include 40 volt, three-phase, three-wire systems, predominantly in the older facilities. You'll see the ungrounded delta systems, the four-wire grounded, and then the high impedance grounded systems, which some of you may or may not have had any experience with. There are some of them out there, and they have some benefits. Sometimes when you get into larger facilities, we have one facility that has 5 400 horsepower legs running at 2300 volts. And you get into, you have very large systems, you get into medium voltage systems where you take a higher voltage from the utility. And then a little bit about low voltage systems when you get below 600 volts. The ungrounded systems, which are still used as the delta systems were originally used because of the continuity of service. The advantage of that is you can get a ground on your system, you can keep running. And so production in a facility is very important. And today's codes requires that you have ground detection indication systems, so you go check it out, and when you're ready to check it out, you shut down equipment and get rid of that ground. However, these ungrounded systems, if you don't do something about it, can be quite catastrophic situations. If you don't fix it and you get another ground, there's some horrific stories out there in the past of like losing every motor in your plant. This is kind of what a diagram looks like down to the nuts and bolts of a three-phase, three-wire system. Your power company will normally give you 3 transformers and bring in 3 wires on the input and 3 wires on the output. The typical 3-phase, 4-wire system is really the predominant power system for all kinds of facilities. In fact, it's so common that as soon as you get much over 25 or 50 horsepower, it's a more common system, and there's so much equipment available for this class of equipment that it becomes the predominant one for any type of industrial system. The drawback of a 4-wire grounded system is when you get a ground, something's going to trip, and it trips immediately. And that means whatever you're doing, you're not doing it anymore. So, but you also get advantage of it, which is more an advantage to commercial building systems, is that there is a 277 volt voltage that's available from the connection of that system. The transformer, you get is connected in this way, and you can take the 277 volts and run lighting. And a lot of commercial buildings use 277 volt lighting because you can put 4,000 watts on a 20 amp circuit at 277 as opposed to 1,600 watts at 120. So you can run a lot of light fixtures in a big office building on one circuit breaker at 277 volt. That's why it's a real popular system in large commercial buildings. But you also see the 480Y systems quite often in industrial facilities and grain facilities. In some regions, there are power companies who, if they provide the transformers, they won't provide delta systems anymore. I have power companies says, if you want power, it's going to be grounded. Why? No ifs, ands, and buts, you're done. So you don't have a choice. So the other thing I like is what I call kind of a hybrid system, which is the high resistance or high C grounded system. This kind of has the benefits of both systems. It's still grounded, but it gives you continuity of service because it's easy to alarm the system and helps control over voltages. One of the problems with the delta systems is when you get a ground at one phase, the other two phases go up to 480 volts to ground, and you find another weak point in the system on insulation, and it punches through the insulation somewhere else, and you have that other ground, and things just go to hell in a handbasket. So the 40 volt Y system, what we do is we take the neutral wire and we run it through a resistor on purpose. And it's a resistor that goes to ground, and there are standard systems for this to actually have, when you have a ground fault, it controls the current to a small, less than 10 ampere fault current. And it senses that, limits the fault current. There's no tripping of breakers. You have the characteristic of a delta system, and where that first ground doesn't trip you, but you have an alarming system, and it controls that voltage shift on the other phases, and so you get the same characteristic and so forth. I've only been able to get one power company to let me ground their neutral like this in the last 30 years. I did it once in California. Usually, to build a high Z system like this, you usually have to have your own transformers to build a system. Most utility companies and metering groups can't seem to figure out that it really won't hurt them if you do it this way. But it does have a lot of advantages of avoiding the ground fault tripping problems and controlling voltages. And I promote this wherever I can. You're seeing more and more of it these days in industrial power systems. Medium voltage systems, like I say, this is only if you get to your really large facilities, typically 4160 or 2400. When you get to the very large horsepower motors, especially when you start getting in excess of 300 or 400 horsepower, all your wire sizes goes down. I mean, you can run a 200 horsepower motor on a number 8 wire as opposed to large 350 kc mill or whatever. I mean, it's a big savings in cost and so forth. You also typically see these types of voltages on trailing cables if you have a mobile ship loader. All your container cranes at most of the shipping ports run on actually trailing cables at 4160 or 2400. But you'll also see that in a lot of mobile ship loaders or unloaders in industrial facilities because you can get a lot of energy through the cable to the ship loader at these voltages. That's a typical place for them. So you only see these on the very largest facilities. When I get into low voltage systems, the standards are the 120, 208, 3-phase 4 wires become a predominantly favorite one. You'll also see these commercial buildings where that's all they have. On smaller buildings, it has the benefit that you get all your 120 volt circuits off of just hooking up between one phase and neutral. You don't have to have any transformers. There's still some single phase systems, a lot of 120, 240 because your homes are built that way. We do a lot of cellular stations, cell towers and stuff, and they all run off of a 200 amp 120, 240 volt service. So there's still a lot of that for small services. The advantage of the 3-phase system is, for the low voltage system, the 208, is if you have a 480 volt power system in your plant and you've got to make your own low voltage. The 208 system is a three-phase transformer, and it keeps the loads balanced on your system, so you don't get a lot of current on one phase versus another phase. Smaller facilities, there's still a lot of advantages to what we call the 120/240 three-phase 4-wire. And what that does, it's a way to connect the transformers so that you get 240-volt three-phase to run some three-phase motors, but you also have some 120/240, and for your single phase, you don't have to put any transformers in to get some lighting circuits or control circuits or things of that nature. So one of the things you have to do when you start planning your power system for your facility is find out, well, where you're going to get the power into to start with, where's your centralized location, a physical location, what's your overall capacity, is it coming off of a overhead pole line, or are they going to bring it in through a trench and conduit, and then who's your power company and who you're going to work with. And other things to get into is cost of service. You know, in these days of rate schedules and deregulated energy choices and voltages, whether it's time of day metering, demand requirements, and even sometimes agreements for usage curtailment, where they come to you and say, well, if you'll agree to cut back your load and take your plant off the grid in our peak periods of time, we're going to give you a special rate. Sometimes that's not very viable if you're trying to load a ship. So, but there are some interests that, and sometimes in standby, if you have any standby generators or generation, we have some utility in Oregon that's doing a distributed generation sharing, where if you have a large standby generator, they will come in and put in equipment so they can bring that generator online to reduce your load and make it like a generation source out on the grid. And they will do all your maintenance, buy all your fuel, and keep up that generator for you just so that they can have access to it, and it gives them some peak shaving capability on the power grid. So sometimes there's opportunities to actually do a partnering agreement with your power service provider to make your generator available as a peak shaving generator into the power grid, and that's a place where you can have some opportunities economically to pay for that. Most regions of the country have deregulated energy choices. It's made rate schedules extremely complicated at times because you have the local utility is your connection to the power grid, but you can have a choice to buy your energy from somewhere else, some other provider. Well, but then the local provider has transmission charges and wheeling charges and other things that go on there because you're buying your electrons from some power plant in Wyoming and buying the energy from them, at least on paper. I still haven't figured out how to keep track of all these electrons, but as to whose is whose. And you're not buying it from your actual local service provider, but based on your consumption and use, they're charging you to get it from them to you. So there's some cost, but in the end, in some cases, there are some people have been able to take multiple facilities. If you have multiple facilities, like 20, 30, 50 facilities that are in the same power company region, and bundle their energy contracts and rate schedules so that, and they buy their energy, and so that they get one big bill every month with all the facilities' energy bills, and for the cost, and then buy their energy from some other provider as one big block for all the energy that they use. It's a lot of work for accountants, I can tell you that. And like I say, as a part of constructing a new facility, sometimes you get into power line extension costs because there's not a pole or a facility nearby, making space for transformers. Sometimes the utility will have some planning charges, and I've even run into some that been quite creative and developed their own system development charges. Have you ever been involved in residential development or commercial development where the city or whatever has a system development charge it's a tax to help develop their infrastructure. I've actually seen some utilities that come up with utility system development charges, charge you another $20,000 just to get their system to your site. It's just a technique for them in the day of deregulation to help reduce their costs. And then when you look at your service connections, you look at, well, who's going to build it, who does what. Usually when you work with them, they'll tell you, well, you're going to put in the concrete, your pad, you're going to put in these transformer conduits, and they'll put in the transformer, or they may run the wire from the transformer to your service, or they may not. So you have to work out all these things in planning your servicing and getting a service into your plant. A little bit about power distribution system design. One of the best things you need to do is minimize your branch circuit run lengths. When I say branch circuit, I mean the final run from the starter to the motor as much as possible. Lighting circuits, you try to get all those brought to the closest place. So those branch circuit runs, the more you can shorten those links and get your service panels or equipment closer to the loads, the less expensive your system will cost. So that gets into looking at where are your motor concentrations, you know. If you have a head house structure, you have cleaning, drying equipment, you have dust equipment, you have a dock facility, rail receiving or loading. Sometimes there are areas where there's a large concentration of motors. You want to try to make multiple, in a larger facility, multiple electrical rooms and get your electrical equipment closer to where those motors are and bring power feeders to them. Because with today's automation, we can tie everything together pretty easily. So just a basic over top view is try to keep your equipment closer to the loads and keep those runs short. As a part of planning, of course, we normally develop one-line diagrams, which just shows you how to get the power flow to equipment, utility power supply, equipment locations, MCCs, all your major motor loads, all your power panels or spot loads. Here's a typical simplified one. We have a utility transformer, revenue meter, main equipment with a main breaker and some feeders, and we're going out to an MCC at a dock, some 40-volt lighting systems for site or whatever, a transformer for controls, transformer for miscellaneous power or an office, and other motor control equipment. I always like to try to keep your control system transformer and your office operational transformer off of your main service. Even if we have to run a 40-volt circuit a ways, some people will just put in an MCC and take a connection off the motor control center to feed your transformer for lighting or controls. I like to be able to shut that MCC down and work on it. If you got issues with your process equipment, you're conveying your motors, it's nice to be able to shut down your process equipment and still have your lights on. And it's just a basic planning thing. If you do it up front, it's not all that expensive. If you just keep those transformers off your MCCs, you can shut down your MCC and do whatever any modification you want to do to it, and still have lights and control power and outlets and all those kinds of things. Like I say, load segregation is important in the designing, dock loads versus plant loads, lighting and control loads. So power metering equipment, power monitoring equipment these days, and as I say, the technology keeps moving on, even in the power industry. You know, it's real easy now to get switchboards and distribution system monitoring equipment that has incredible information, data logging, connections by even Ethernet with monitoring software where you can pull up on a screen more information than you'd ever want to know about your electrical system sometimes, but you can do your own energy monitoring, power factor. They even, most of the instrument power system electronic meters you can get for your main equipment will also tell you if you have harmonics in your system too, which is a whole other issue as a result of the predominance of variable frequency drives. And a lot of these meters have communications and remote monitoring capabilities. And then we have a lot of new equipment now that are designed as arc resistant with all the things going on with arc flash safety and protection. The manufacturers have come up with entire designs of equipment specially built to create arc resistant features for safety to reduce your maintenance requirements and increase your arc flash safety. Here's another piece of equipment from Siemens, and here's an example of their equipment. And you'll see they actually have venting in the top of the equipment, and the equipment's been designed, and most of these companies have complete presentations as how they design this equipment. So that if there is an arc flash event within the equipment, it actually directs all the arcing stuff up through a venting system up through the top of the equipment and takes it away from the people working on it. And the breaker compartments are compartmentalized and isolated, and a lot of things are done to take that arc flash and keep it away from coming out of the front of the equipment and take it up the top of the equipment. Now, you do have to be concerned about what's above that equipment when you do this, because you don't want to like start your building on fire when the arc flash goes out the top. But and I will tell you that a lot of the new arc flash type of electrical equipment that's available, it's not the same price. So I mean, you're going to talk anywhere from a 20 to 40% premium on buying arc flash resistant equipment versus standard equipment. So it's kind of like a safety, conservatism, and how much do you want to spend type of exercise. But that equipment is out there now. So, and like I say, with the circuit breakers themselves, a lot of the circuit breakers are a whole package of electronics for their protection and tripping. We have circuit breakers now that have tripping characteristics that has a maintenance mode switch. And so you can actually, with a special switch, and sometimes they're external and internal, the electrician can flip a switch, and that breaker was like set so that it wouldn't trip in coordination with downstream equipment, but he needs to work on it. And he can flip a switch, and the tripping characteristic of the breaker changes to another setting automatically that's been configured to reduce his PPE requirement on the arc flash level. So we actually have breakers with multiple tripping characteristics, so you can switch it into a maintenance mode and reduce your arc flash and safety requirements. Let alone the breaker itself is available with complete energy. You can get breakers now with built-in energy monitoring on that breaker, harmonics monitoring. You can even get remote communications, and you can actually tie in all your circuit breakers and not just have a meter on your main, but you could have energy monitoring and data on every one of your feeders if you want to. And I'm sure you'll love to sit around and just look at meter displays on your desktop, but those capabilities are here today. You can see what your loads are in the circuit, how many amps you're pulling, kilowatt hours, just a whole plethora. And it will even do some data logging of a harmonic event or a fault event. If you get a fault event, it will actually, some of them will do transient capture of a fault event and save the last 30 seconds of data. Here's an example of a electronic breaker from Siemens. Here's another look of one that has some modular tripping modules that can be put under the breakers. Here's another one from Eaton showing a screwdriver adjustment for the maintenance off-on switch for the tripping curve. So we get into some other stuff that's critical to the operations, which is the solid-state motor controller, the reduced voltage starter, the solid-state soft starter, the various terms for that, typically used for soft starting large motors. Sometimes your power company, when you work with them, will have requirements that you have reduced voltage starting or reduced current starting of large motor loads because it affects the voltage out on the grid. So you're required to do it sometimes. But I've seen a real, the place where you see a lot of it is reducing mechanical shock on equipment. I've heard of cases where starting a drag on a soft starter will actually save a lot on the mechanical shock. And in one facility, it was breaking chains periodically on the drive system with full voltage starting, put in a soft starter, and never had another problem. So it can actually help you with some, for mechanical reasons on the equipment. With soft starters, even with soft starters, there is a capability for some energy conservation. A lot of them have a control mode where when the motor drops back, if the conveyor is running empty, it actually drops back the excitation voltage slightly on the motor and reduces the actual energy into the motor and makes it run more efficiently when it's running at light currents. So you can actually get some energy conservation out of some of the soft starter technologies. Now, a lot of the soft starters today, they're getting smaller and smaller and smaller. But a lot of that's because they have built into them now a mechanical bypass. And so the original technology was all a solid state controller controlling your motor. Most of them have internal mechanical bypasses because once you get it up to speed, because you're just starting it with a soft starter, if you can bypass electronics and take them out of the circuit, it's more energy efficient itself. And you're not using the solid state circuits to run the motor, and then the duty on the solid state circuits, they can make them smaller, less expensive, and once you get up to speed, a lot of them have a built-in bypass now right in the soft starter. In the old days, we used to do that with an external contactor. Once we get up to speed, we'd pull in a bypass contactor to take it out of the circuit to run it at full voltage. They do work, there's not, but a more effective technology, of course, is our VFDs, solid state adjustable speed motor controls. Continuing to see the cost curves and physical size of VFDs coming down as they're being promulgated throughout the whole electrical industry. And we see them more and more and more. And a lot of applications for them, and they don't cost you an arm and leg anymore. You do have some other issues with them if you put too many of them on your system, but of course, obviously, applications are, of course, variable feeders for cleaners. You have variable speed feeders for blending applications, for different product flow types, for receiving systems. And in vector drives, if you use constant torque vector drives, it's the best method for starting a conveyor under load. I mean, a soft starter has some capabilities for doing kickstart and trying to get a conveyor up and going, but it doesn't come close to what you can do with a vector drive. I mean, you can run that motor with a vector drive with a lot of extra torque up to the breakdown torque when you have to start a piece of equipment under load, and it's the best motor control technology for starting loaded conveyors. We look at where there's opportunities on dust fans, and where there may be a case where you have a dust collection fan and you have multiple collection points and there are actually dampers on the system, where sometimes you're sharing collection with a truck receiving that's not always in operation with something else. And when you have variable conditions, you can get energy conservation by reducing the airflow, still meeting your CFM requirements as your collection system is being used in different modes of operation. We've actually seen projects like that at some facilities in Oregon through an energy trust group of utilities, where they actually do studies, and they give you money to help pay for it because it reduces energy. It's the energy conservation opportunity on the power grid. Sometimes it just mechanically is not functional, but and then all the VFDs today, I mean, they all have capabilities of remote communication, Ethernet, control, and so forth. And like I say, I'm not going to get too much into the automation side of this because we have a really good speaker coming up on that. But a lot of the power systems technology now is becoming integrated and is implementing better controls. Electronic motor overload systems. Now, almost all manufacturers now, their standard overload is becoming an electronic motor overload versus the old melding alloy heater elements and so forth. And they have a lot of capabilities. Some of them even have communications so that you can get down to an overload relay on an individual motor starter. In fact, the Siemens ones, I'll show you a picture here, have some of them have auxiliary inputs on them. Like if you want to do some motor winding temperature analog into the overload relay instead of into the control circuitry. They can do remote communications. They have jogging mode configurations and so forth. Here's a picture of a standalone Siemens. There's a whole bunch of little switches on the upper right-hand side of that lower overload electronic relay for different functions you can turn on and off. And one of the standard features on that overload relay is ground fault. So you have a ground fault sensor built into your overload relay. It's actually, technically, it was a no-brainer to do that. But what that gives you is, if there's a ground on your motor, the overload relay senses it and trips the starter instead of relying upon an upstream circuit breaker. And now you can coordinate a ground fault on a motor with your system so you don't take a breaker that takes out the entire MCC. So you can actually have stage ground fault systems right down to your motor starters with the electronic overload systems. The other advantages too is the overload relays cover a range of motor sizes. I don't know if you've ever, people get involved, you change out a motor, you go from a 15 to a 25 horsepower motor, which at 40 fits on the same size starter. But the overload relay heater device has to be changed out to match the nameplate current of the motor to protect the motor. Here you just change the dial. You move the dial on the overload relay to the proper setting for the full load current, and you're done. Got to put a little bit bigger wire, but other than that, it makes upgrades and so forth, and the range of selections and setting up your overload relay. You don't have all these boxes of little heater elements that you have to find the right number and match it up to some table and so forth. It makes the whole startup, commissioning, and configuration a lot easier. Here's some more examples of overload relay systems. This isn't a real good picture, but I just want to point out that we also have arc flash MCC gear. All the manufacturers, Eaton, Siemens, Square D, they've all come out with new arc flash MCC equipment, arc flash resistant. And they've done a lot of features in their buckets to isolate the exposure. And one of the problems you have in a standard MCC starter bucket is when you plug it in, it's got some stabs that plug into the bus, and there's little wires that come in off the bus into the breaker. When we do arc flash studies, your exposure is those wires coming in from the bus. And that could be a 600 amp bus or 800 amp bus. So if you get a tool up in there on those wires, just turning off the breaker, you have a little piece of wire that's live coming off the bus. So that's a hazard. And they've done things in these buckets to isolate that hazard, to put a guard or enclosure around it. And some of them have racking systems where you can rack it out partially and disconnect it from the power bus and so forth. So a lot of different features to reduce the arc flash hazard within the starter bucket if you have to work on it. And once again, it does come at a premium. I mean, there's a pretty good premium on that style of equipment. I mean, if you'd ever work on equipment totally turned off and racked off, you wouldn't have pulled out, it wouldn't be a problem. But sometimes that's just not practical. I haven't figured out how to measure a circuit when it's turned off. So one of the biggest issues you have with your whole arc flash access safety is if you want to do an infrared scan. You can't do an infrared scan if it's off. The only way you can do infrared scan is when the current's flowing through the circuits. So it's kind of a catch-22 of, I have to open the door to do my infrared scan, but the label on it says I have to wear this whole suit to open the door. And so it gets to be a real issue in some of those cases. Here's a picture of a stack of a arc flash MCC. They don't look too different. I'm going to get a little bit into lighting technology before I run out of time here. Of course, over the time we've had, a lot of the sources are fluorescent sources. We've had the new PL lamps, curlicue lamps. You even see those in the miniature style in your home. T8, T5 lamps, electronic ballasts, and so forth. And then the other ones are what we call the HID class of sources. Mercury vapor, I'm almost going to have to take this off the slide. I don't think anybody, you might have an old enough facility to have some old mercury vapor bulbs. They actually might still be glowing, but putting out about 10% of the light without failing. But so I would look into, I don't know if you can even buy mercury vapor lamps anymore, but the latest technology in HID is the metal halide and high pressure sodium stuff. The metal halide is the white type of light, which is a much better color and so forth. High pressure sodium is that yellowish looking lamp, very efficient, has reasonable color. But the lighting industry is becoming LED. This is where it's at. We work in many environments, including commercial buildings, and all the R&D and development of new technology is in LED lamp sources. And it's going to become, it's moving so fast. I never believed it could move as fast just in the last 2 years. The number of products that come online, and even equipment I specified last year, I can now get that same equipment with the same amount of light with 20% less energy into that same piece of equipment. And they're making the efficiencies higher with the drivers, and we have equipment right now that's available for industrial fixtures and hazardous ratings. All the R&D is going in. I know one manufacturer that was bringing 42 new or revised products to the marketplace, and only 2 of them were non-LED. And this is the wave of the future and where it's all going. And there's probably power companies that will pay you to put LED lighting in to save energy. They even have retrofit kits for lighting troughers in commercial buildings that will pull out the guts and put in a driver and LED lighting system for offices without replacing the entire fixture. And so we're looking at retrofit and new systems. Here's an example of some equipment that's available right now. Looks like standard industrial equipment, but it's got LED lamps in it, lamp systems. Here's a NEMA 4X Class 2 Div 1, Div 2 fixture that you can go out and buy right now. So I'll get a little bit into hazardous location issues, as you've heard before with dust and so forth. In the electrical world, we have a relationship to 61, and obviously in NFPA 70, the National Electrical Code, Articles 500, 502, 504 covers dust hazard location wiring requirements. There's another standard, NFPA 499, that I use quite frequently, and even though the title says for petrochemical facilities, the principles are the same, but it is a standard for methodologies of classification for hazardous dust. 497 is for gases, 499 is for dust. It's a whole standard just on the whole background and methodologies for, hey, am I class 2, am I division 1, am I division 2? Just a whole background. It has a lot of valuable information for practices and approaches. So there's actually some International Society of Automation has their own practice standards, 12.10, so there's another whole standards industry, mainly the instrumentation guys, and that's used quite a bit in a lot of the petrochemical guys like using the ISA standards and so forth. So, and of course, classification principles, whether it's an enclosed area, the dust accumulation, which has been talked about in other discussions, whether it's present normally or abnormally, it gets into whether Division 1 means you think it's going to normally be present no matter what you can do at some periods of time. And Division 2 is you've got everything enclosed, good dust control, good housekeeping, and you say, well, it's going to be only if something goes wrong. If I get hazardous dust accumulation, then it becomes Division 2. The interesting thing about all these codes and standards is that NFPA 70 is a construction standard. In our committee that I'm on the code panel for electrical code on has 500, 502, 504. We set the methodology for how materials are classified and what the requirements are for electrical wiring. But then other committees set what the criteria is for the materials. And so it's kind of like we said, well, we're going to make dust class 2. We're going to say it's agricultural dust, and well, there's coal dust and some other things too. But and then so we determine the classification for the purposes of electrical classification, and other standard groups set the standards for what those materials are and which ones are combustible and so forth and so on. NFPA 49 actually has a whole table of typical materials, a whole materials list of all kinds of materials and dust, and different characteristics, their minimum explosivity, a whole bunch of technical data where you can go down the list, flour, wheat, and many other materials in it. So you say, if you know what material you're handling, you can go there and say, yeah, this is a class 2 material. One thing we do when we do have the hazardous locations is we try to put our major equipment in, if they're in the area, in pressurized rooms. And fortunately, in a dust hazard area, it's very easy to get a clean source of air, pressurize the room. You only need 1/10 of an inch static and certain velocity requirements if you open the doors. And if you pressurize the room with a clean source of air, it's non-hazardous. And so you can put anything you want in there. So the basic technique is get those load centers, stick a room in your shipping gallery and pressurize it. And then you can put anything you want in there, run all your wires, and just run a feeder back to your main equipment. Of course, as soon as you get into the hazardous areas, you get into specially rated equipment, hazardous location equipment. It is dust ignition proof is the proper terminology. People say it's explosion proof. That's class 1. That is a defined term in the code. Explosion proof is gases, dust ignition proof is dust. And then the other technique is intrinsically safe equipment, where there's a lot of controls and stuff where we can run, and a lot of your temperature cable systems are engineered to be intrinsically safe inherently, and have interfaces for that, but there's a lot of other ways with barriers and relays where you can handle that. Other thing to pay attention to, you can't forget about static electricity control. Everybody's familiar with the conductive belting that's required, and whenever you have belts and so forth. Bonding and grounding is, you need to make sure everything's tied together, because you don't want to be having static electricity building up a charge somewhere, especially inside an enclosed belt where you know you're going to have dust. So I only have a few minutes left, and whatever you want to talk about, I'm available. I'll talk about arc flash or anything. So, have any other interests or questions?
Question for Mark.
It's been a lot of fun with all the new technology that's coming out with lamp sources and VFDs and so forth. That yeah. Good. The question is on VFD drives if there's any special provisions or whatever for lockout and tag out. Okay, lockout and tagout in FPA 70E, you lock out the breaker. A control circuit stop lock is not a lockout. It's not legal. It's not an appropriate lockout. The only legal lockout is the main 480 volt or 230 volt power source to the drive. And it's the same as it's always been. So if you take a standard motor control circuit and you use a stop button as a lockout, I can show you how I can open up the door with a screwdriver and turn that motor on without any electrical energy, because all the mechanical contactors have a mechanical override, and I can shove that thing in and run that equipment. That's why a control circuit lockout is not a legal lockout. It's got to be the circuit breaker. So it doesn't matter whether it's a drive, a starter, a soft starter, you need to lock out the circuit breaker and kill everything.
Any other questions for Mark?
Thank you.